Hello everyone and welcome to another session of the Digital WE Days. My name is Hirston and I will moderate this webinar today. Our topic of today is passive components challenges in AI systems. Our speaker today is Thomas Zednicek from Passive Components. Thomas, hello and welcome. Cool to have you here. AI hardware demands extreme power and precision. But how do your passive components keep it up with the pace? Let's uncover the challenges. Stage is yours, Thomas.
Good afternoon. My name is Tomáš Zednicek from European Passive Components Institute, and today I would like to present the passive component challenges in AI systems. And after short introduction, we will have a look into AI power management, GPU development, and then what it means for passive components, what are the consequences, selection guides, technologies, and then we will also look a little bit behind horizon. As an introduction, the passive components, of course, depend strongly to the development of semiconductor devices, what's going on in this field. On our present development on the processor side, there is a continuous trend in increasing clock speed and also a reducing of the supply voltage. So this trend makes capacitors job decoupling more critical, also with an increase of the frequency and increase of dI per dt current spikes. So in the consequences to this, we can see requirements for capacitors to lower the parasitic losses, cell inductance, low ESR, and also its capability to handle higher power capabilities. In the past, as a processor capacitor, we have seen most of the electrolytics, but moving to MLCC class 2 capacitors, now to class 1 silicon capacitors, and in the future, it will be necessary to use more integrated solutions on chip to have components closer to ICs to reduce parasitics and allow even higher currents. This can be illustrated by development of MLCC capacitor types from its self-inductance point of view, from conventional types to reverse geometry and sweet terminal devices and other constructions that further reduce self-inductance and enable operation at higher frequencies. The second trend in semiconductors is a move towards wide gap semiconductors in the era of higher voltages and higher frequencies. The technologies coming here are silicon carbide, gallium nitride solutions that can operate at higher frequencies. This is associated with reduction of components and also change in the selection guide of components. In an example by ST Micro, as we can see on the slide on the top side, there is a redesign of the board from the conventional silicon IC to gallium nitride and showing a reduction of board space, so increasing the frequency and cost saving associated with reduction of number of components. On the other hand, there will be some more challenges for inductors and challenges for stabilization of gate drive. So, for example, for tantalum capacitors that offer stability, there is opportunity for gate drive circuits. Looking now at the trend in AI, energy, and power management. If we look at the current market, the AI demand stays very strong through this year. Bottlenecks shifted from the processor itself to the power capacity and floor space. The older generation now for GPUs for AI servers is Nvidia H100, which is now available in lead time about 10 weeks. The upcoming generations is B200 that is available from end of last year and currently in the mass supply. The next generation will be available end of this year, the Blackwell Ultra, that offer significantly high computing power. If you look what is the current consumption of such GPUs, the AI GPUs is significantly higher power consumption compared to the standard CPUs, GPUs seen in the normal PC and computers. These CPUs has a consumption around 340 watts. The first generation of Nvidia H100 has a consumption around 700 watts, but the current generation H200 has reached around 1200 watts. For curiosity, you can guess how many watts require a human brain for human intelligence. So it's around 20 watts. So this presents a high increase in energy required to feed the AI data centers. AI data centers consumption already present around 2% of the global usage of energy, and this share is increasing. This also require further power generation increase, and following the source Statista, it looks that up to 2030 there is a balance between global power generation and AI data centers consumption. But the truth is that share of the energy consumed by data centers is continuously increasing. If we compare AI server performance for current and upcoming generation in 2 years' time, we can see the significant increase in computing power, but also increase in consumption. On the other hand, the performance forecasted for next 2 years increase about 5 times compared to consumption, that is 1.5 times. So this is amazing technology improvement that is going to happen within next 2 years. Nevertheless, we have to be ready for a rack consumption reaching around 130, 140 kilowatts. So how to address these challenges? So there are a couple of countermeasures that these AI hardware designers are using. The first thing is to move up with the power rack voltage. Some servers are still using around 12 volt on the motherboard. So this voltage will shift to 48 or 54 volt motherboard architecture. Where not all circuits will be able to run at 48 volt. Some storage drive will still require 12 volt, so there will be some local DC-DC converters to drive some peripherals, etc. But overall, the shift to 48 volt power rack architecture aims to reduce around 30% in conversion losses and over 16 times less power distribution losses. The next step is move to 800 volt architecture on the power source side. This was announced by Nvidia in spring 2025 that Nvidia is coming into discussion with semiconductor manufacturers how to enable this transition starting from 2027 in order to enable support of over 1 megawatt IT racks. The key efficiency gains are 5% improvement in end-to-end power efficiency, maintenance cost reduced up to 70%, lower cooling expenses, and cost reduction due to lower usage of copper. Another change is regarding to memory. architecture moved to DDR5 memory system. DDR5 architecture offers up to 50% higher data rate, 10 to 20% better energy efficiency, greater capacity, and improved communication speed. The challenge limitation is that it requires complete change of architecture and redesign of the board. What are consequences to passive electronic components? At first, we see boost in demand for MLCC and its development. For manufacturers, we see they decide that AI servers require 10 to 20,000 ceramic capacitors on board compared to 2000. So there is a 10 to 15 times fold increase in number of capacitors. How to achieve this? There is a strong demand for miniaturization achieved by technology improvement in finer grain ceramic materials, more uniform dispersions, avoid impurities, etc., and thinning of dielectrics, as well as working on new dielectric materials. We can see releases of very high CV ceramic capacitors trying to address various challenges. This is the example of GPU-CPU coupling, where ceramic capacitors try to even replace conventional bulk capacitors, in this case SP-cap aluminum capacitors, by release of new high CV ceramics. We can see latest releases 220 microfarad 4 volt in 1206, 330 microfarad in 1210 at 2.5 volt. That should go directly to the processor coupling. And they mentioned something as an effective capacitance, because these capacitors, class 2, has a strong dependence of capacitance with DC voltage and AC voltage. They may get together a much higher capacitance compared to SP cap, but at the operating conditions, they achieve similar capacitance. And with this, they promise to offer downsizing and lower ESR compared to aluminum polymer capacitors. Another challenge associated with the shift of memory architecture to DDR5 is that DDR5 already has a voltage regulator inside of the chip. So in DDR4, we had a voltage regulator outside of the chip, moving 12 volts to low voltage, using 10 microfarad 4 or 6.3 volt MLCC or tantalum capacitor. In DDR5, we have a 12 volt line, so we require 25 volt capacitors from MLCC to get better stability of capacitance. What is released in this field are 22 microfarad 25 volts already in 0805 with effective capacitance around 10 microfarad. 48 to 52 volt rack power voltage is another example of latest development of ceramics towards higher and higher CVs. We see releases from Samsung, Murata, TDK of 100 volt ceramic capacitors with very high CV, 1 microfarad to 10 microfarad. On 1210, there may be some concern of risk of cracks. Samsung tried to address this with molded frame MLCC on such larger case sizes. The other manufacturers offer smaller case sizes with higher CV. The 800 volts power supply architecture present the challenge for semiconductors and passive components. The 800 volt is in the zone with very highly competitive semiconductor choices between silicon carbide, gallium nitride, and conventional silicon. Moving towards wide gap semiconductor represent faster reaction, higher frequency, speed of these semiconductors, but this is also associated with faster peak and spikes that has to be filtered out. So snubber capacitor is more necessary. Again, we can see a couple of examples of passive components that are dedicated to such wide gap semiconductors. In this illustration is Murata that mentions a specific testing for double pulse load that is typically associated with 800 volt silicon carbide configuration, and the company testing such parts up to over 1000 volt to be able to effectively suppress any spikes of this. The other components are circuit protection devices and safety capacitors, where the appropriate creepage distance has to be set up to increase reliability and capability to withstand the high voltages of such components. On the CPU-GPU coupling side, we see the challenge between silicon capacitors and ceramic capacitors. So on the side of silicon capacitors, we can see the design with quite high capacitance density, up to 2.5 microfarad per millimeter square, that can be used inside of packaging or underneath the packaging directly with the die, that offer ultra-low self-inductance with single-digit picohenries, ultra-low ESR with capability to place very close proximity to the chips. On MLCC side, we see the other push for 0201 capacitors with a standard size that can be also used in such applications, and relatively high CV, again 4.7 microfarad, 2.5 volt MLCC in 0201. If we calculate capacitor density, then using the maximum capacitance, it would end up with 26 microfarad per millimeter square. But at the operating conditions, the effective capacitance maybe somewhere like 7.2 microfarad per millimeter square. So this is higher compared to silicon capacitors. On the other hand, the silicon capacitors are very stable, stable capacitance with voltage, temperature, and can be used to very highly demanding applications and mission-critical applications. On the power supply management side, you can see also use of aluminum polymer chip capacitors or tantalum polymer chip capacitors in desktop computers or notebook computers. Then the main voltages are 12 volt line, and then low voltage on processor side. The 12 volt line is stabilized using usually tantalum polymer chip capacitors, which are now ready to transform to 48 volt with availability of new high CV at 6375 volt low ESR capacitors. On the low voltage aluminum polymer side, we can see extension of lifetimes of such capacitors, and such capacitors, of course, offer very high stability of capacitance with temperature and with time. There is also one impact of AI to the power grids. What was observed is the sudden spikes in consumption and potential issues with instability and the need for additional infrastructure to stabilize the power grids. Because the power scale of sudden spikes can be in 100 watts, megawatts, even to gigawatts. And this is a very unique load that has not been seen so far in power grid reliability requirements. In past, we have seen some power energy storage systems based on battery technologies that helps to stabilize regenerative power sources, etc. But for AI, this is not sufficient from 2 points of view. First is the speed. We need a very quickly reaction. And second is cycle lifetime, which is on battery is very limited. So this is opportunity for supercapacitor and introduction of supercapacitor storage systems. We already see some of the solution that is coming from supercapacitor manufacturer like Skeleton that offers now their Skeleton server boards, claiming they reduce the power requirements by 40% and increase also computing power up to 40%. Also, we see this from Nvidia latest announcement about power supply for GB300 server that consists of supercapacitors. We don't know the exact number of supercapacitors. This was not disclosed, but if we do the calculation to cover 200 to 500 milliseconds of 125 kilowatt rack, then the approximate need for supercapacitors is between 50 to 100 cells. So typically we can assume that is 100 supercapacitor cells per rack. So this may boost and drive supercapacitor demand in the near future. On side of inductors, there is also forecast that demand value for power inductors for data centers increase 2.5 times by 2030. So what are the inductor requirements? Is course higher current handling that is transferred to a higher saturation current needed. Greater power density, you need a compact form factors, low parasitics, low DC resistance, high frequency performance, need excellent high frequency characteristics, and was high thermostability over time without degradation. So this may call for new material innovation, new core materials based on nanocrystalline alloys with a high magnetic flux density, smaller, more efficient inductors, and also with potential for integration inside of chip or under the package. As an example of technologies on inductors under consideration, these are nanocrystal material composite magnetic materials that feature very high saturation, so they keep stable inductance across high power. Nevertheless, in comparison to manganese zinc ferrite cores, they have lower inductance. So there are still advantages of ferrites in some applications. On ferrite side, what is the growing technology is the inductors with flat wire that increase saturation current up to 25% at relatively low core losses. Another technology for AI servers are one-turn inductors. What is the advantage? They support quite high switching frequency. They have advantages in DC optimization with reduced losses, DC losses, and for AC also with reduced AC losses. Low loss inductors can be found also in other part of the complete AI networking infrastructure. So of course, to reach the complete speed, we need fast transceivers across the various devices, from server up to the user. The fast solution is in optical transceivers. They will also use low-loss components capable to operate at high frequency. In an example, here is a release from TDK of an inductor for optical transceiver, claiming DC resistance reduced by 70% and significant increase in saturation current. On resistor side, there is requirements for current sense resistors with higher continuous current and steeper slew rates, thin film chip resistors in small dimensions 0402, even 0201, with higher pulse handling and better heat dissipation. Everything has to be controlled in temperature, so thermistors has to be here. They are critical for inrush current limiting, and varistors to protect against voltage surges, especially on this 800-watt line. And this move to this wide gap semiconductor is also requiring lower parasitic inductance and stable high frequency performance for resistors. Talking about some concrete releases and concrete chips, we see some high precision tight tolerance specification down to 0.01% and TCR values as low as 25 ppm or even better. Better film resistors, high power thin film chip resistors, and resistors with superior noise characteristics. 0201, 0402 chips are already available. We can see some examples of thin film, high power aluminum nitride chips from TT Electronics. We see 4-terminal shunt resistors with extreme low resistance from Yageo, power metal strip resistors from Vishay, or a high power density current sense chip resistors from Stackpole as an example of such resistors for AI. For future, for what are the enabling technology, one of this example is memristor. I know we talk about this technology for a long time. Memristor was forecasted in 1971 as a fourth missing passive component, where the function of resistance depends on the amount of charge coming through the component. So how it operates: when current flows in one direction, the resistance increases. When it flows in the opposite direction, the resistance decreases. And this change in resistance is retained even after the current is turned off, and so then it's called memory resistor. Typical construction consists thin film material like titanium dioxide sandwiched between two metal electrodes. Nevertheless, these components are not yet in mass use. The issues were in reproducibility, manufacturability, and stability of these materials. Nevertheless, last year we have seen some work together with TDK and Tohoku University in Japan that demonstrated new version of memristor. They call it SPIM memristor, and claim they achieved AI board with power consumption of 1/100th of the standard watts needed for AI power. So in mid to longer term, this may be the solution to further reduce the power consumption of AI devices. So in summary, AI challenge for hardware is mainly in power demand. AI systems, GPUs and servers, they exceed 1,200 watts power energy requirements. And our rack, we are talking over 130 kilowatts by 2026. Key is now the efficiency to reduce this power consumption as much as possible, because this is current main bottleneck of adoption of large AI data centers. The industry is moving from 12 volt to 48 volt power rack voltage and exploring 800 volt power supply systems in next future. Impact on passive components. In general, for all components is needed to work at a higher frequency, lower its parasitic, and increase the frequency range. And it's capable to work reliably, long-term, continuously in higher thermal load. It calls for development of new materials like nanocrystalline alloys for inductors, or new dielectric materials for ceramic capacitors, to be able to answer the need for wide gap semiconductors and the trend on GPU coupling. For energy storage evolution, supercapacitors may see some significant increase in demand for stabilization of energy storage associated with operation of AI, because it's causing very dynamic energy spikes. In longer term horizon, there are good hopes to reduce further the consumption using promising technologies of memory stores that are forecasted to significantly reduce the consumption of memory modules. That's all from my side, and thank you for your attention.
Yeah, thank you, Thomas, for your interesting presentation. Now we will come to your questions. Before we start with the live Q&A, I will share the handout from Thomas, and then everyone can download it. Yeah. Thomas, are you ready for the questions?
Yes, I am. Good afternoon.
Perfect. Okay, then I think we can directly start with the first question. Do you see a potential for NSEC ceramic capacitors to replace aluminum polymer chip capacitors in GPU bulk coupling?
Yeah, thank you. It's interesting question. Of course, ceramic capacitors were trying to replace the other capacitor technologies for some time, and it has been like shooting on moving targets. So with the improvement of electrolytic capacitors, this was not an easy job. On the other hand, what we see, the rate of the speed of the development of MLCC is much more progressing compared to electrolytic capacitors. Like 2 years ago, like ceramic capacitors achieved the same rated values of capacitance and voltage or similar. But the truth is that due to the capacitance dependence on voltage and other things, the reality was different, that the real application capacitance was much lower. But today we are in a situation where ceramic capacitor manufacturers start talking about what they call effective capacitance, which is a capacitance at the operating conditions. And this starts to be similar to aluminum or electric capacitors. On the other hand, purely technologically, still the electrolytic capacitors provide a stable results stable capacitance with AC voltage and DC voltage. But with the progress of MLCC and motivation for downsizing, this starts to be very tough battle.
Okay, thank you, Thomas. Then next question from Benedict. As you mentioned, 800 volt isolated power supply. Do you think this voltage will increase even more in the future as the power demand is rising? And will therefore the border between power parts and computer parts be extinct?
I think we will stay in 800 volt for some time. It's still the planned main power supply feature, because Nvidia raised this challenge this springtime with necessary talking with semiconductor suppliers, how they can see the availability of semiconductor power capability on 800 volt to answer the demand up to nearly 1 megawatt, which should be sufficient for 800 volt. And the timeline for this is that Nvidia count this to be used on systems from 2027. And I think for some time we hope to be sufficient with 1 megawatt power of the AI. So I think with 800 volt we are done for some time.
Mm-hmm. Thank you. Then I see one last question in the chat. Do you see synergy between AI server and automotive application requirements?
Yeah, this is a very good question. 800 volt we know already from electric vehicles, so it's quite nice synergy of the rack voltages and the components that are ready to work on such high voltages. And the industry, the component industry, already has a development based on the automotive electrical vehicles, as I mentioned, and but also the industry high voltages for regenerative power generation, solar, wind, etc. And towards the 800 volts. So it's nice synergy. And another nice synergy is for 48 volt rail, which is also used in automotive and the industry of the components. There's already wide choice of components which comply to automotive standards, which is very nice thing, because automotive became in fact the standard requirements for qualification of components. Now, regardless if the component is used in automotive or other standards, now most of the manufacturer qualified their product now to automotive ACQ 200 standards. So these components are ready, 48 volt, 800 volt. So I think the AI server can follow this very nicely.
Okay, thank you. Then one question. What is this app note about and who wrote it?
The app was written by myself, and actually this presentation about AI I prepared for a PCNS conference, which was in September in Sevilla, and also supported by technical paper. So in the app note you can see the text related to this presentation.
Okay, thank you. Then I see no more questions in the chat. Yeah, when you have any questions, write into the chat, and then Thomas will answer them via email in the next days. So yeah, thank you, Thomas, for your presentation, for your time, and for
you're welcome. Thanks for organizing, Marcus, and thanks everyone for joining and interest in this topic.
Yeah, thank you for your attention. I hope you enjoyed it. Now I will share the link to our homepage at the Digital WE Days. So check it out. Register now. Today is finish day 3. So tomorrow we had the last day with 8 important and interesting sessions. So check it out. Register now, and hopefully you see us in our next session. Thank you. Have a nice day, and bye-bye.
Thank you. Bye-bye.